Today's teaching challenger is a scientist and big thinker whose mind focuses on the minute building blocks of life and the universe. Nuclear physicist Dr. Paul Stevenson.
Nuclear physics gets kind of a bad press in a sense because if people think about nuclear physics they think of weapons and radioactive waste and all that kind of stuff. And while that's obviously something that nuclear physics is involved in, it actually has lots of really positive uses, like it's used in a lot in medicine for cancer treatment, for things like magnetic resonance imaging is all based on understanding how nuclear physics works. It's just one of many applications of physics that hopefully some of the kids will get interested in.
And the kids he'll be facing will be a GCSE top set science group from Year 10 at Uckfield Community Technology College in East Sussex, with the help of their teacher, Joanne Yates.
I'm hoping that Dr. Stevenson will inspire the children who find physics difficult, and I think that's mostly the girls in this group. They feel that physics isn't for them and they just can't see how it applies to them and what they could do with it. They can see what they could do with biology and they can see what they could do with chemistry, but physics, they don't see it. So hopefully he will inspire and enthuse those girls, and maybe some of the boys too.
Okay, so how does one plan a lesson for GCSE level pupils?
Well, first of all we need to think about what we want to get across to them in the session. So what were you planning to do to start the lesson off with then?
Well, my research is in nuclear physics and I sort of don't know really how much they already know about nuclei. I'm guessing they know that everything's sort of made of atoms.
No, they've got quite good atomic structure knowledge.
But I'm guessing they don't know that much about, say, different isotopes.
They will know a little bit about isotopes, but I don't think they will be very confident in talking about them. So that'd be great if you could get them to be a bit more confident and talk about that.
I think it's a nice story to tell about nuclei, that you can have something that's an element that they may be familiar with, like carbon, but that it comes in different varieties because it can have different nuclei and they get put to different uses.
So we could do it as a lesson where it's thinking about these uses, an applied sort of lesson.
Well, I haven't brought radioactive samples or anything like that with me, so how will I get them to start looking at isotopes and thinking about them?
Well, I think what would be a good idea is if we split them up into groups and give them a name of an isotope just to start thinking about and talking about, and then maybe they can brainstorm ideas about where they might have heard of the word before or what element it might be linked to or something like that, so that they can just start thinking about it.
Yeah, so it might be worth making sure we pick an isotope that gets used in, say, medical imaging, and so that has sort of obvious benefit to, well, to everyone that ever needs to go for medical treatment or for scanning. Yeah,
maybe then that could be in part of the plenary or something. We could draw out some of the ideas from the children about how they would use these isotopes in a future career maybe, or how you've used them in your own career, and start talking about that with them so that maybe we can get them enthused about becoming nuclear physicists.
Yeah, okay, that sounds like no problem.
I'll leave you to have a little think about it. I'll go get the class, bring them in, and we can do it.
Okay.
Right guys, this is Dr. Paul Stevenson. He's come to talk to you today about being a physicist and what he does in his professional role. So I would like you to listen to him very carefully and ask him lots of questions at the end, okay? So it's over to you.
Okay, thanks very much. Afternoon, everyone. So just to get going, just to give me an idea of how much you know about things like nuclear physics, I just wanted to kick off by asking you to get one of these. If you want to help distribute them, that would be fantastic. If you were to line up as many atoms as it took to make a line 1 centimetre long, how many atoms would you need to make that line 1 centimetre long? Yes?
1 million?
Write it on the, write it on, on the whiteboard. Okay, I see some numbers appearing already. So each atom is roughly 10 to the minus 10 meters. So there's a couple of you there had 100 million, so well done to you. So if an atom is about 10 to the minus 10 meters, that's 0.00009 zeros after the decimal point, then 1. Anyone know how big a nucleus is across? This is the thing at the center. Yeah.
10 to the power of 10.
Okay, it's not 10 to the power of 10. So an atom is 10 to the power of minus 10 meters, and a nucleus is going to be smaller, so it's going to have to be a smaller number. Yeah, over there.
Is it 10 to the power of minus 12?
That's better guess because it's smaller than an atom. It's actually, nuclei are really, I mean, although atoms are just made of nothing but electrons and their nuclei in the center, the nuclei are 100,000 times smaller than the atoms, so they're really, really tiny things right in the center. So it's 10 to the minus 15 meters is about the typical size of a nucleus. Okay, so
Whilst our minds boggle at the size of nuclei, Dr. Stevenson is already moving on to the main part of his lesson, isotopes.
Okay, so you guys here have polonium-210, hydrogen-1, uranium-235, carbon-14, hydrogen-3, which is also known as tritium.
So you're going for polonium-210. Have you heard that word before? Maybe in the news.
Was it the thing that killed the Russian
Maybe.
guy?
Write down.
Killed the Russians.
So there's hydrogen-1, which one of the other groups have, and hydrogen-2, which also gets called deuterium. But it means that tritium nucleus will only live for about 12 years, and then it will just decay.
Could they use it for nuclear energy?
Yes, they're trying to use it for nuclear energy. All the nuclear energy we get at the moment comes from fission reactors, where they take uranium and make it fission, which means split up into two lighter nuclei, and that releases energy.
You can use uranium in power stations, can't you?
Yeah, but we don't know why it's used in power stations. So.
Yeah, but because it doesn't give off carbon dioxide, does it?
Yeah, and it's used in bombs as well, so we know it's chemical.
It's like,
I wonder how you can find extract it though.
Yeah, and is it in the body or not?
If you join the whole atom, including the electrons, then yeah, you should have 6 electrons on the outside. You've got 8, but, because the electrons have to balance the protons, not the neutrons.
Is hydrogen only found in the water, or is it found in the air as well?
So hydrogen as an element can be, but we're talking about hydrogen-1, which is the isotope hydrogen, different to the element hydrogen.
kills Russian spies.
Yeah, waste product.
They don't just use it, do
It's not
they?
that, mate. That's just like one big thing and then somebody died.
That's what I know.
Okay, class. So I've been around a couple of the groups, and you've all been had lots of good ideas about what these isotopes are used for. I didn't get round to all of you. Nevertheless, I'm going to ask you all to nominate one spokesperson to come up and present what you know about the isotope. Thanks for volunteering. Do you want to tell the rest of the class what you found out about polonium-210?
We figured out that it killed a Russian spy a while ago. It was a heavy metal and a waste product of nuclear power, possibly.
Yep, I think that's all correct.
We had hydrogen-1,
Okay.
and we know it's used in fuel cells, and we weren't sure, but we thought it was very reactive. And it's found in water, but it can also be in the form of a gas.
Okay, we had uranium-235.
Okay.
You can split the atom, and when it's split, it is used in nuclear power stations.
We did carbon-14 and we found out that it has 6 protons and 8 neutrons.
We had hydrogen-3, also called tritium. It glows in the dark, and any formed in the Big Bang would have decayed by now.
So do you know what the 210 means and the polonium? What does that say about the nucleus?
Not sure.
Uranium, actually, I think it's element 92, so it has 92 protons. I better check that. It is actually the most important nucleus used for medical imaging. So if you go for an MRI scan, it's hydrogen-1 that gets used most of all. So this is a sort of like the periodic table for the elements, but this is for the isotopes. So every single element has a line in this chart, and then there are many boxes along the lines that give us all the different isotopes. Okay, well done everyone. I'm glad you managed to find out some interesting things about the isotopes. This is just a very narrow area of physics in a sense. Physics encompasses all sorts of things, not just nuclear physics. But just from that part of physics, I think there are lots of interesting applications, lots of interesting jobs you can go into along the medical side, the energy side, or so on. But really, I'd much prefer it if we could spend the last few minutes you asking me any questions.
How could you locate plutonium or uranium?
I'm not sure I should tell you that. You're after some uranium and plutonium. No, it's okay. Well, I mean, it's a sort of mineralogical thing. You look for the kind of rocks that they contain. There's a common ore of uranium called pitchblende, so you just look for where there are deposits of that. A lot of the uranium in the world comes from Australia. A lot of the stuff that we use comes from Australia because they just have large deposits of the rock.
You know, you said about cosmic rays falling from space. Would they be quite hard and scarce to find on Earth?
Cosmic rays are mostly made of protons and some neutrons that have come from a long way. And actually, so passing through us now, there's a whole lot of muons that come from high up in the atmosphere. So if we had a muon detector, which is just a lump of plastic basically with a photosensitive shielding that picks up light, the muons will go through this plastic detector. It will cause electrons to be knocked out, and you'll see flashes of light, and you actually can count the number of muons that are coming from outer space. So there's muons going through us right now.
Are there a lot of jobs in nuclear physics?
In nuclear physics specifically, there are jobs in areas like nuclear medicine and nuclear power, and then there are jobs doing what I'm doing, being in a university doing research into sort of fundamental nuclear physics, the forces between protons and neutrons. But if you go to university to do a degree, you don't study just nuclear physics, you study all of physics. And from that, so at my university, our students go to all sorts of different jobs, like banking, like computing-related things. A lot of them go on to scientific research of all sorts, so lots and lots of different scientific fields. Physics students are really, really in demand by employers because they're very numerate and they have really good problem-solving skills, because doing physics is about seeing new situations, trying to solve new problems. And so really, we have a very, very good employment rate in physics. Okay, so to wrap up, I just really want to thank you for giving me the opportunity to come along and talk about nuclear physics. It's been a lot of fun for me, so I'd just like to thank you, really.
Thank you.
Thank you.
After the class, it's time for our guest to look back on the lesson with Joe Yates.
So let's have a look at the starter activity. How do you think that went?
I thought it went well. I mean, everyone took part, which is, I think, a good sign. They all thought of numbers and they all came up with fairly reasonable numbers, so they obviously already had some idea of how big atoms were, roughly. I mean, I wasn't expecting everyone to just come up with the right answer, but I thought that was good. And it was a nice sort of breaker into the whole session.
So moving on to the main activity, when they were discussing the different isotopes, how do you feel that went?
Again, I was a bit worried that just writing down the name of an isotope, they just wouldn't know where to begin. So I was quite pleased that, with a little bit of prompting from us, that they were able to come up, they did know sort of reasonable things about the different isotopes. I mean, nuclear properties as well, not just atomic properties. When they came up and stood and gave their talks, I was really pleased actually with how confident they all were when they spoke.
And so when it came to the plenary activity, when you were talking, trying to bring everything together, do you feel that that brought everything that we spoke about in the lesson together? Or?
I think so. I probably didn't say as much as I could because I sort of wanted to give them another opportunity to ask questions. And I probably didn't come up with as many examples of great jobs you can do with nuclear physics. I always think of more afterwards, but yeah, I think that probably went okay. So do you think they'll be able to relate what I talked about to their curriculum?
I would think so, and I'd hope so, and hopefully over time we'll be able to refer back to it and talk about it, and in months to come hopefully we'll see the fruits of your work today, with them being enthused about things to do with nuclear physics and asking questions, so that'd be great.
I enjoyed the lesson today because you learnt about everyday nuclear physics. I enjoyed learning about the facts and the different isotopes. I thought it was very educational, and it's now helped me to learn about future jobs which might hold for me when I'm older.
I really enjoyed how he told us all the different uses of hydrogen. I didn't know there were so many, and I'm definitely going to pay more attention in physics from now on.